what's the angle of an equilateral triangle? So if your high school math isn't fresh in your head, you might be forgiven for not knowing this. But what do people do when they want to find out the answer to that question? Of course, the standard way nowadays is to go to a search engine like Google, type in the question, find some website that contains the answer, and then sort of read that website and answer the question from there. Now, the goal of this paper here is to do the same thing, but in a machine way. So the machine would see this question right here, and it will be able to get additional textual knowledge from a corpus and consult that, and then at the end come up with the answer, which is 60 degrees right here. This type of task is called open question answering, so like OpenQA or OQA, and the distinction here between this and the previous kind of tasks that were often called question answering is that usually in question answering you simply have a question and then you have either no help at all, so the model just has to answer the question, and things like GPT-3 demonstrated that that is actually something that's possible if you have a large enough model. Or much more common, you would provide the question and then one document, and you would sort of guarantee that the answer is somewhere in this particular document. So even though the task was called question answering, it was more like a machine reading task, because you knew, okay, all I have to do is I have to find the answer somewhere in the document to this particular question. So the task was more kind of a pattern matching sort of approach. Here, the task really comes close to what humans understand as question answering. Namely, you get a question, you want an answer, and it's open in the sense that the machine can go with the question to like a search engine. I have no clue how to draw a globe. To a search engine, get multiple documents that would help it kind of rank them and so on. It's basically able to use a search engine and then answer the question from there. So that's what we're going to look at today. There has been a lot of work. I'm not saying this task is new. There has been a lot of work in open domain question answering, and this is one of the latest incarnations of it. The paper is called Realm or Realm. I'm really not sure how to pronounce this. The word would be called Realm, I guess. It's Retrieval Augmented Language Model Pre-Training by Kelvin Gu, Kenton Lee, Zora Tung, Panopong Pazupat, and Mingwei Chung. So the paper is first and foremost about a pre-training method, as you can see right in the title. So the entire system that's presented here has sort of been explored in papers before. Like other papers have already done this, or we retrieve other documents, and in this particular case, as you'll see, the documents are retrieved using inner product search through a pre-embedded through corpus, which is usually Wikipedia. So you'll see all of this. The new thing about this paper, just to make this clear, is the way that the pre-training works for these systems. We're going to look at the entire architecture, but just such that you're aware of what's really coming from here and what's gathered from what's kind of conglomerated from what worked so far. So the improvements here are pretty stunning that they achieve with this new pre-training method, which is pretty cool considering that it's the new thing is a pre-training method. So we'll look at this, we'll look at the architecture, the pre-training method, the kind of hacks that you need to get it to work, and finally the results. As always, if you enjoy content like this, don't hesitate to share it out and subscribe if you are not already. And with that, let's jump in. So the abstract says that language model pre-training has been shown to capture a surprising amount of world knowledge, crucial for NLP tasks such as question answering. And here again, we say question answering is kind of the broad category of anywhere where you have to answer a textual question. So what do they mean by world knowledge? What they mean by world knowledge, they mean something like the question that we considered What's the angle of an equilateral triangle? You can't, from the question itself, you can't answer the question. It's not like a little math question where you just have to do the correct calculations or so on, or which one is the longest words of the following words. It really is additional knowledge that you had to have learned somewhere. So that's what we call world knowledge. And the fact that an equilateral triangle has 60-degree angles, you need to have picked that up from somewhere. Now, if you are GPT-3, then what you have done is you've taken this giant corpus, right? And you just did language modeling on it, and that gives you GPT-3. Now, that means since GPT-3 is so huge, that means that all the world knowledge that is contained in this corpus is baked into the model and can be sort of parsed out with good querying. So if you provide a correct query, you can sort of parse out what's in the weights of the model. But it's very intransparent in the weights of the model. It's baked together with the language modeling. They are criticizing, not criticizing, but sort of arguing against this right here. They say, however, this knowledge is stored implicitly in the parameters of a neural network, requiring ever larger networks to cover more facts. To capture knowledge in a more modular and interpretable way, we augment language model pre-training with a latent knowledge retriever, which allows the model to retrieve and attend over documents from a large corpus such as Wikipedia. And used during pre-training, fine-tuning, and inference. For the first time, we show how to pre-train such a knowledge retriever in an unsupervised manner, using masked language modeling as a learning signal and backpropagating through a retrieval step that considers millions of documents. Okay, so there's a lot of information here. So first of all, what they want to say is they want to say that in such a corpus, there are two kinds of knowledge, right? There is language, and there is this world knowledge, okay? And they want to make this sort of separate. So they want to have a model that can go to the corpus, retrieve documents, and then use those documents. So whereas previously the world knowledge has been joined with the language model, they want to sever this connection, say we want a model where we can simply teach it to go look for information. We can teach it to go search for things, and then the searched things will inform its answering of the question. Okay, so that's what these systems are trying to achieve. And we saw that before in the diagram. So they say we augment language model pre-training with a latent knowledge retriever, which allows the model to retrieve and attend over documents from a large corpus. And also they use this masked language modeling as a pre-training, as a learning signal, and backpropagating through the retrieval step. Now this is the interesting part right here. So what you'll have is you'll have a question, and we can actually look at this diagram right here. So the pre-training is going to be masked language modeling, okay? Ultimately, what you want to do is what we looked at before. Ultimately, what you want to do is question answering. So this thing right here, where the input is a query, and then you want to retrieve documents, and then you want to join them. And let's actually draw this up. So you have a query, and you want to retrieve documents. How do you do that? You train an embedding for the query, which is usually a BERT model. Like that's the fashionable thing to do. If you don't know what BERT is, I've made a video about BERT. But basically BERT can take a piece of text and then it will output a vector or multiple vectors for it. In this case, we just need one single vector for the entire query. Okay, and then you have a bunch of documents in your corpus. So in your corpus right here, you have Z1, Z2, and so on. And what you want to do is you want to embed all of those. So you want to have B of Z1 and B of Z2. Okay, You want to embed all of those documents, and then you want to compare these embeddings. And you want to retrieve the document that's most relevant for your question, right? If your question is about equilateral triangles, the angle in them, then there's probably going to be like a Wikipedia article of triangles or equilateral triangles specifically. So this corpus right here, we're going to consider this to be Wikipedia. Now, ultimately, especially like a company like Google would like this to be the entire internet. But for these tasks, for the academic tasks, this is often a limited corpus. And then the data sets are also made such that they can often be answered with that limited corpus. But in essence, this could be the entire internet. But for now, it's Wikipedia. So we want to embed every single document in Wikipedia and then compare them using the inner product. So you train your model to, first of all, take this corpus and then assign each member of the corpus a vector. So this could be Z1, this could be Z2, this could be Z3, and so on. And you want to train it in such a way that if you have a query, then the query will be very close in inner product space to the document that's relevant. So the query might be your question about the angles, and the document right here might be the document about triangles. Okay, and this document might be the document about, I don't know, England. And this one right here might be the document about, I don't know, weightlifting. I have no idea. Like just random Wikipedia documents. Okay, so you want them to be, let's draw a little dumbbell right here. So you want the other documents to be far apart from the query. So you train two things. You train this model right here, which is the embedding of the corpus, okay? And you train this model right here, which is the embedding of the query. These are two separate models. And then you want the inner product between the two to be small, to be large, whenever the document is relevant for answering the query, and you want them to be far apart whenever it is not. Now the question is, of course, how do you know when it is relevant, when it is not? Because you have to have some training signal right here, right? You have to basically know in advance which documents are relevant, and you don't. So they start out with this masked language model pre-training, which we see up here. The masked language model pre-training does the following. So this is unsupervised. You take some string, right, like this one, and then you mask out a token. This comes straight from BERT. Right? You mask out a token, and then your goal is simply to reproduce that token. Okay. So if we were in BERT, you would forget about all of this. You would simply try to predict what the mask token is. But here we say, well, we allow the model to use additional context in order to fill in the blank. And you can see already how this is going to help later. But okay, so we take this sentence and we allow it to retrieve documents. And maybe the document retrieved is this one right here. The pyramidion on top allows for less material higher up the pyramid. And then you concatenate the input. The input is this right here with the mask token, as you can see here. You concatenate that together with this thing, which is this thing right here. And then you train a different model to take this as an input and tell you what the mask token is. Now, if the retriever is good, then this model has a pretty easy job, because here you see at the top, something is at the top, and here you see the pyramidion is on top, then it becomes fairly easy. Okay, the question again, of course, is how do you teach the retriever to do well? And this is somewhat of a loop. So formally, the knowledge retriever right here is we're going to model this distribution as a joint distribution. Sorry, this is down here. All right, so here the central formula is this. What you want is a model that takes in a question, or in pre-training a masked string, and it produces the answer, or in pre-training this is going to be the masked token. So this is going to be the question and this is the answer, or this is going to be the masked string and this is going to be the token that has been masked from the string. Okay. Now you're saying I can decompose this probability distribution into the following probability distribution. And here we take z as a latent variable, usually, but here z is the document, okay? So what we want is a model that takes in your question and a document that is relevant for answering the question, and from that it produces the answer. And in order to fill our probability distribution, we have to have this other model that takes in the question and outputs a document. Okay, so this here is the retriever, and this here is going to be the answerer. And in order to make this the valid probability distribution, you need to marginalize over all of the documents in your corpus. So now you can see how you train this. You simply retrieve you train this model here to predict which documents are relevant to a certain degree in a backpropagatable way, so in a continuous fashion. Assign each document a probability to be relevant for answering this particular question. And then you take each of the documents and answer the question why from it, and you marginalize over all the documents in your data set, and then you get a final probability, and all of this is completely differentiable. The problem, of course, is that, especially in this paper here, there are like 13 million documents, so you won't be able to train very far according to that. So let's look at the individual parts. First of all, this knowledge retriever. The knowledge retriever model is a model that will take in a question and a document and tell you how relevant that document is for this particular question. And this, as you can see, is defined as a probability distribution, specifically here this exponential distribution of f. And what is f? We've already seen f is simply the inner product between the embedding and of the question and the document. So that's the kind of thing we drew before, where the document is supposed to have a high inner product with the query that it is relevant to, and a low with all the other queries. Now, since they cannot take all of the documents, what they do is simply they go in. So at the beginning, if let's say you're somewhere during training, right? And you have this index built up of all of the documents. What you'll do is you'll project your query into this space and you retrieve the couple of documents that are closest to the query, okay? And you only use those. So you sample a few documents. This is the same thing that we do in, contrastive pre-training and so on. It's just taken here to the retrieval mode. So you don't marginalize over all documents because that would be computationally too hard. You simply marginalize over all the documents that have a reasonably high inner product with the query that you're considering. Why does that make sense? Because if you look at any other, like this one here, the inner product is going to be almost zero. So the inner product with the query is going to be almost zero. So it does not contribute at all to this probability right here, which also means that the gradient is going to be fairly small. Now, even though the gradient is fairly small, it can still be that you haven't learned something good yet, and actually the document would be pretty relevant for that query. And because you never use it to train, you will never ever recover it, because you don't ever use it to train. There's no gradient flowing to it, and so on. So you're sort of relying on this being sort of self-organizing, like over time. These turn out to not really be relevant because you've learned something stupid, and then your query embedding either would change the query, maybe during training, change the query more towards the direction of the relevant documents, or the relevant documents themselves would sort of shift and push each other around and so on. So you're kind of relying on effects like this, but there's definitely a death spiral that can go on. So they address this right here, and yeah, they address this right here. Here, the key computational challenge is that marginal probability Py of x, which is this one, involves the summation over all documents in the knowledge corpus Z. We approximate this instead by summing over the top k documents with the highest probability under this retrieval step. This is reasonable if most documents have near zero probability. Even with this approximation, we still need an efficient way to find the top k documents. Note that the ordering of documents is the same as under the relevance score, okay? Which is an inner product. Thus, we can employ maximum inner product search algorithms to find the approximate top k documents using a running time storage space that scales sublinearly with the number of documents. So there are these algorithms to do maximum inner product search, which you can use to find the top k documents. To employ these algorithms, we must pre-compute the embedding, so all the embedding of the documents in the corpus. We must pre-compute them for every Z, and construct an efficient search index over these embeddings. So this now becomes very much like a search engine, where you have to have your corpus and you have to build an index in order to find things fast in there. Like, it looks easy in our 2D examples, but to find maximum inner products in high dimensional space is actually a very challenging task. However, this data structure will no longer be consistent with this retrieval thing, right? Because as we train it, our index is going to be old. So as we train it, our index might change, but if we only build it once, then that's of no use if the parameters of the embedding are later updated. Hence, the search index goes stale after every gradient update on theta. Our solution is to refresh the index by asynchronously re-embedding and re-indexing all the documents every several hundred training steps. And they have a drawing of this right here. So they have two different jobs. The trainer here trains, updates itself using the old index. So an index for a couple of hundred steps. Then every couple of hundred steps, it sends over its new weights. And the index builder builds a new index using these new weights, right? And then the process starts again. These can run in parallel, as you can imagine. So as soon as the index builder is done, it sends over the new index, retrieves the new parameters, and starts again building an index. Because ideally, you want to rebuild the index after every single step. But of course, that's going to waste too much time as well. So that was the retriever step. The actual answerer step is fairly easy. So once you've retrieved good documents, right, now you don't need, as we said, you don't need all the documents. Where are we at? Right here. We're not going to do this with all the documents anymore. We'll simply retrieve the most relevant documents because that's going to approximate this sum fairly well. The answerer here, that's pretty simple. That's going to be just a BERT model that takes in Z and X. Okay, so this is going to be another BERT model that's going to take in the retrieved document and the question, and it's going to output Y. Now, how does that look? In case of the masked language model, we've already seen it, right? You simply would input, where is it? You simply would input the concatenation of the two, with the mask, as you can see right here, and then the output is going to classify, be a classification task. So in the case of Bert, you have your query right here as text, and then you have your document Z right here, and there somewhere would be a mask token. You would put Bert on top of that, everything together, and then at the position of the mask token, you would do a classification across all of your vocabulary, right, and see which word is most likely. And that's how you train that and evaluate that. If you are in the fine-tuning mode, then you don't have masks anymore. So what you would put is your query right here and your document that you retrieved, and then you would simply output. Now here is an assumption, and the assumption is often baked into these data sets. You assume that if you have the correct document, the answer is somewhere in the Z document right here. So Y is somewhere in here, and what you would do is you would classify the start and the end of the span of Y, right? These correspond to these. So that's your training signal right there. As I said, this is not always the case, but very often, especially in these data sets, it's the case that it is a single contiguous span as the answer. Okay, so that's basically the architecture. As I said, the architecture is using inner product to retrieving top whatever K documents. In this case, I think it's about 5. They retrieve 5 documents. For each document, they run it through this BERT in this joint way, like on the bottom, and then they classify the output. And you can do it with the top 1 document, but you can marginalize over the top documents for both pre-training and for actually answering a question. There's lots of stuff you can do. The important thing right here is that this thing is what the paper proposes anew. It's basically saying, how do we do masked language modeling pre-training with a system like this? All right. Okay. And the rest of the paper basically goes into more detail, like how do you join, exactly, what's the input right here? And we've already seen you just concatenate whatever you have. You concatenate your query and your documents and so on. So the important thing is it's 2 distinct, like there are 3 models right here, right? Model 1 is used to take a document from the corpus and map it into a vector in this vector space right here. Okay, that's model 1. That is the model that you want to build this index for, right? Every now and then you take that model and build an index for your whole corpus. Then model 2 is the model that takes a query, okay, a question to answer or a masked string, and also generates a vector in this vector space right here, okay? That is a different model than the model that embeds the document, and you don't build indices for that. You continuously train it, and you just, because you only need to embed every query once, and if you were to not build an index for model 1, then you would need to re-embed the whole corpus for every training step. And then model 3 is something yet completely different. Model 3 takes whatever documents you retrieved right here as Z, along with the query as text. So not the vectors, but it takes the text of these documents, and it takes the text of the query, and it produces an answer Y, which is either the mask token or the answer span in the document. Okay, but this is, again, this is a text model. This has nothing to do with the vectors from before. All right, so that was the architecture and the pre-training. Now they go into a few details. Namely, first detail is how do you actually, how do you even see that this does something sensible, okay? And thereby they analyze the gradient of this thing. So if you look at the gradient, here's the gradient of the of py of x. Py is, this is, as we said, the answer, and this is the question. And this probability distribution has everything in it we've discussed before, like retrieving the documents and then marginalizing over the retrieved documents and so on. Okay, so here you can see that the gradient is, first of all, it goes into the direction of this inner product. Okay, this f here, that's the inner product between the embeddings of x and the relevant documents z, or relevant according to their relevance. Okay, so the gradient of the entire model goes into the direction of the gradient of the inner product. So that's already a good thing, right? Now we can ask ourselves, when do we want the gradient of the entire model to be strongly correlated with the gradient of this inner product, and when not? That of course depends on the document itself, and this quantity R specifies how much that is. So if this turns out like we want it, then we can say, okay, the training of this model does something sensible. So what's this quantity R? The quantity R notably has this ratio right here, this ratio -1. Now what does it say? If the top of the fraction is larger than the bottom of the fraction, then this is a positive number, right? And if the bottom is larger, then this is a negative number. Okay, so let's look at the two elements. The ratio basically means that the difference here is this z. So the ratio is larger than 1 if the probability of the answer rises when you have z in there versus when you do not have z, right? Here there is no z. So what it basically means is that the document helps. If the document helps for answering the question x, then that probability is larger than the bottom probability. If the document is irrelevant, then that's 1, right? And the entire thing becomes 0 and therefore no gradient. And if the document is counterproductive, and that's often the case actually, because these documents, they can introduce noise. Like noise is often counterproductive for these systems because you have more input, and then the distribution of y will become more noisy and therefore flatter, and this fraction would be lower than 1, so this is going to be negative. So this quantity is positive the more relevant, the easier it is to answer the question with y given the document. And that's exactly what we want out of a system like this. So if you look at the gradient of the system, it shows you that what we want to happen, namely that the system is trained in such a way that the relevant documents will help, it is actually happening. Okay, so that's the left hand side, and there's a little bit to be said about this thing right here. The probability, this is proportional always to the probability that your retriever outputs this document. Okay, so this quantity R is going to be even larger if your retriever outputs that document frequently. So if it is a helpful document and the retriever outputs it very frequently for the given question, then this quantity R is super large, and that's exactly what we want, right? Okay, so the next thing they do is they have to sort of take care of the initialization here, because the problem we've spoken of before is that if your retriever is bad, right, it will not retrieve the good documents, and so it won't retrieve this z here very often. And then it really doesn't matter what this quantity is right here. because this is going to be very low, like even if it hits upon a correct document. And probably it doesn't, because there's like 13 million documents and you retrieve 5 or so. So very probably you're not by chance going to hit the correct document. So you never have a chance to get the document that would actually help you answering the question. Then you get a bad gradient, then you screw everything up even more, and so on. So the problem is that if you just train this from scratch, you have a pretty bad learning signal. So what they do is they have to take care of initialization. So they have to initialize things such that they are already working fairly well before anything else happens. And this is sort of, if I had to, criticize these systems a bit, it's that there are many hacks to getting them to work, right? You have to really take care of initialization and so on, because they sort of build in a loop, right? The better the retriever, the better the model that can answer the question. And the better the model that can answer the question, the better gradient you get for the retriever. But the retriever only samples, so it doesn't even see all the documents. So how can it ever learn that a given document is going to be relevant if it never sees it, and so on? So there's quite an interdependence, and you only can do that with good initialization, as is the case for a lot of these language tasks. But here, even the pre-training, so that's the point, even the masked language model pre-training, where they already have this retrieval step in there, even that needs to be itself initialized at a good point. Otherwise it doesn't help. Otherwise, because you want to train the retriever such that the masked language model becomes easier, and you have to take care of a bunch of stuff. So here they say, at the beginning of training, if the retriever does not have good embeddings, the retrieved documents will likely be unrelated to X. This causes the knowledge augmented encoder to learn to ignore the retrieved documents. Okay, so it basically just falls back to a model that does not have these other documents, because none of the retrieved documents are relevant. Once this occurs, the knowledge retriever does not receive a meaningful gradient and cannot improve, creating a vicious cycle. To avoid this cold start problem, we warm start the embedding of the input and the doc. So these are models 1 and 2, right? I think this is what I called model 1, this is what I called model 2. Using a simple training objective known as the inverse closed task, where given a sentence, the model is trained to retrieve the document where that sentence came from. We refer to this paper. So this paper, I believe, is the Orca paper. And just quickly, for the knowledge augmented encoder, we warm started with BERT pre-training. So this here, I think this is model 3. So this is model 1, this here is model 2, that's model 3. So this paper here, I believe that's the Orca paper. The Orca paper is very, very close to this paper. It also has this retrieval step and so on, but it said that it introduced this inverse closed task as pre-training for its own model. So you can see this paper right here as sort of an evolution where they go from Orca and basically use that as an initialization for their own model. Now, it's not exactly the same and so on, but this inverse closed task in that Orca paper was quite a central point. So what you want to do is you simply take a document from your corpus, any document, and then you select a span, like this span right here, and then you make two things out of that. First of all, the span is going to become your X, okay? And then the document right here, the document, but without the span, obviously, so the span you just leave empty, that's going to become the thing to retrieve. And you simply now train a model, your models. So in this case, this is model 1 and this is model 2. You train them such that the inner product between the two, so your embedding of X times your embedding of Z is going to be large. I guess they have a weight matrices in front of that, but it doesn't matter. So you can see that you train the model to retrieve the document where a piece of text came from. Okay, and you train these model in conjunction with each other. You simply make the inner products large, and you can do negative sampling for this in order to contrast this with other documents where the text isn't from. If you don't know what negative sampling is, I've done a bunch of papers, most notably the Word to Vec paper, where that was sort of introduced. So that's your pre-training task, and I'm going to just take a wild guess here, and I'm going to guess that in this ICT pre-training task, this here is started from the public BERT checkpoint or something like this. So technically, this you have the masked language model of models 1 and 2 would be the pre-training, and then this ICT would be the pre-training, and then the masked language modeling with the retriever built on ICT is going to be the pre-training, and then the question answering using that retriever is going to be the actual training. Okay, so there's a lot of build up here. One thing to say is that, yeah, as you see here, so here is this pre-training on the left, unsupervised, where you simply, again, the way you have to think about it is, what document do I have to retrieve to make the job of filling in the blank here easier? Okay, and the hope is that that correlates well with the job of what document do I have to retrieve to answering the question easier. Okay, and what document do I have to retrieve to make the job for the model that answers the question easier? I guess that's the way of formulating it. All right, so the next few things you have to do to get it to work is prohibiting trivial retrievals. They say if the pre-training corpus and the knowledge corpus are the same, which I guess they sometimes are, because, you know, it pays off to do the pre-training on the same corpus as your knowledge corpus if it is large enough. A trivial retrieval candidate Z that is too informative, right? There exists a trivial retrieval candidate. If the masked sentence comes from document Z, the knowledge augmented encoder can trivially predict Y by looking at the unmasked version of it. Yes, of course. Like if you do this masked language modeling and you take your sentence from that corpus, then the retriever can simply go look for that document, and then it becomes very, very easy to fill in the blank, right? Because you just do this pattern matching. And that's of no use, because what you want to teach the model essentially is to kind of look at the semantics of a document. So you simply prohibit that particular thing. So this is during pre-training. This is for your masked language modeling pre-training, what we call here realm pre-training. During that, you simply prohibit. For this reason, we exclude this trivial candidate during pre-training. So that's one thing you have to do. And I feel here is, you know, where the specifics of your task and your data set come in, because, you know, on the internet many things are copied and sort of copied and translated and so on. So if you were to do this not in Wikipedia but in a more unstructured way, this would be one of the pain points, I guess, because imagine, you know, there is just a website that translates all the other websites to French. And then your model can simply learn to translate from French and always retrieve the French document and fill in the blank using that. It will learn nothing about the word. Like, it will not acquire any retrieval along semantics of world knowledge. It will simply learn to translate to French and so on. So I think that this is rather more crucial than this simple one paragraph appears to have it. Then they also introduced this null document along with the things they retrieve. So if they retrieve maybe not 5 but 8, I think they retrieve 8 in the experiments. If they retrieve, so they retrieve 7 documents, the 7 closest ones in inner product space, plus a null document, such that the model has the opportunity to ignore all the documents, right? So it can basically just go to the null document, assign a large weight to that, and just answer the question outright. So if the answer is already contained in the question itself. It can just, point to that. It doesn't need an additional document to answer the question. So they leave room for this possibility right here. Now, this would also be a good metric to assess how much the model makes use of the other documents, and I think they have this further down. And then the last thing here is the salient span masking. So when you do masked language model pre-training, what you'll do is simply you'll drop out not even words, but word pieces, right? So so here, let's say this, you have this span of text. What you do is you just drop out like at random words, or as I said, even worse, if this is BERT or something, you have word pieces. So you maybe just drop out this CUS right here and the low. Now, people have observed that this is now pretty easy for the model, and most notably, it doesn't require a lot of world knowledge. It doesn't require even a lot of attention to the other parts of the sentence, which is what you would like to induce with this pre-training. All you basically need to do is you need to say, there is something, and then cal. And maybe you look at the words around it, and you can pretty easily deduce that it's local. Also, to fo on, you can pretty easily deduce that's to focus. So this kind of pre-training doesn't really mean the model learns some long-range dependencies or understands language pretty well. So people have been upping the kind of smartness with which they drop out things. So the most obvious thing is to drop out entire words. Even though BERT works in word pieces, you can simply always enforce that entire words are dropped out. Now it's a bit harder. Then what people do is like salient span dropouts, and that's what they do right here. So what you want to do is you want to drop out things that are sort of kind of little snippets that belong together. So for example, if I drop here local context, if I drop this out, right, then I need, some masculine spans only require what, right? And that requires much more world knowledge to answer that question. It requires much more long-range dependency resolution in my language model and so on in order to see that there's world knowledge. And this is exactly what you want to induce here, right? You want to induce your model to learn more global knowledge, more world knowledge, more semantics of the language. And you can relate this to sort of pre-training or data augmentation, I'd say, in vision. For example, there you have the random cropping. So you only crop out part of the picture and then you crop out another part, maybe here, and then you ask the model, does this come from the same or from different images, these two parts? And the more you crop, sort of, the more the model has to, cannot rely on just single pixels somewhere, but actually has to understand image scenes and so on, what direction is up and whatnot. So we see qualitative difference between pre-training methods and augmentation methods for images. It only makes sense that we see a qualitative difference and differently induced inductive priors in text if we do this. So what they do is they say, since we want to induce this kind of thing, we will not only drop out entire words, we actually drop out entire salient spans, such as, right, United Kingdom or July 1969. We use a BERT-based tagger to identify named entities and a regular expression to identify dates. We select and mask one of these salient spans within a sentence for the masked language modeling task. We show that this significantly outperforms other masking strategies in section 4.5. Now, while I agree with the notion of salient span masking, I have big troubles with the way they do it here. And I think this is where you kind of start to overfit on the particular data set. So I guess they looked at the data set and, you kind of, as a developer, you kind of look at your, just what kind of questions are there. And they saw, often it's, questions about entities, question about dates and so on. So, we can just pre-train with those things in mind. And that's where it gets a bit wonky and really specific to your task, really specific to your data sets and so on, to do that. So this is already baking in a bit of knowledge, or a lot of knowledge, I would argue, about the task itself. And we're going to see that this is actually fairly important in the results, the salient span masking. And it's sort of, I get it, you get better numbers with it, but also it's kind of dirty and very specified to the task. I want to actually see, and I don't know if people have done this, but the way I would do it in a kind of more principled way is, if you have a piece of text, what you do is you start by masking one word, okay? Like I'm asked spans here. And then I would ask my own model, right? My own half-trained model, which if I want to predict this one, right? If I want to do masked language model with this one, I can use one of these saliency methods to ask which other words are most relevant to predicting this one, okay? And it will probably say, okay, salient is really important, right? Because if I know that there is salient in front of it, I can predict that there's spans really easily. And then I can say, well, okay, so I'll mask salient as well. Now I have masked these two. And I do that up to some threshold, right? So the saliency in my mind should come directly from the model you're training. By that, you're basically saying that, model, you've sort of learned your local dependencies. Now I want you to go beyond that. So you're basically really mean to the model. You forbid it from using everything it has learned so far to make the task more challenging and more challenging over time. I think this is kind of a built-in curriculum learning, and that's how what I would see. If this is already done, maybe someone's already done it. Just let me know in the comments if this already exists, kind of expanding the masks by assessing the model's own saliency. All right, so let's jump into the results. And the results, as you've already maybe seen in the abstract, are pretty good. So on these open domain questioning data sets, they outperform all the previous state of the art, not only by a little, but by significant margins, as you can see here. And they do it when both the pre-training corpus is the same as the knowledge corpus, and when the pre-training corpus is actually a different one. That tends to work actually even better in 2 of the 3 tasks. So fairly cool. Also not more parameters than previous models, especially not this T5. So this T5 here is an example of just where everything is baked into the language model, whereas I believe these models right here, they have retrievers along with it. Yeah, you can see here they all have retrievers along with it, but their pre-training objective and their architecture sometimes is different. Now, I believe you can also see the fact here that Orca has the same amount of parameters. It's very close to the model right here. It's just that the pre-training here is different. And you also see right here, they do some ablations where they say, okay, how important are the different parts right here? So you can see on the development set, you get your 38.2 exact match score. If you only train the retriever, but you reset the encoder before, so that's the thing that actually answers the question. If you reset that before fine-tuning, you drop a little bit. If you reset the retriever, you drop more. But still, I would say it's fairly competitive, as you can see. Now, this is probably the test set, but still it's fairly competitive right here with the previous state of the art. Oh yeah, here is the baseline. It's 31.3. Now, interestingly, as you can see right here, if you have uniform masks or random span masks, which is the 2 types of masking that I discussed, where either you drop out just word pieces or entire words or entire spans. So you just you just take that idea further. You say, well, I'll mask an entire span, but nothing with their saliency. So no regexes for dates, no entity taggers, and so on. You drop quite a bit, especially with the uniform masks you see here. you drop quite a bit. Now with the random span masks, you drop for the random spans, and then you drop again for the uniform masks. So this seems to be pretty important. So never forget when you see things like this that there are these engineering choices that can make as big a difference as the actual idea in the paper itself. Okay, so you can see this is the improvement is, it's like 3 points from uniform masks to random span masks, and then 3 points again from the random span masks to the realm pre-training. And the actual improvement with the uniform masks over the baseline right here is not as high. Now the baseline, uses a different thing. It uses this ICT as pre-training, but still I haven't seen the saliency masking. Maybe I've seen it, maybe it's somewhere else, but I haven't seen it. Okay, they also have an interesting thing right here. They also have an interesting plot in the appendix where they show the performance of the different masking styles with respect to this retrieval utility. And the retrieval utility compares these two things that we've looked at. So it compares how good is document Z in answering the question why versus this null document. So the null document is basically just answer the why, right? So if let's play devil's advocate and say that all of this retrieval stuff, it's just bollocks, right? The knowledge is still baked into the language model. We were critical that this helps and so on. Then this would also always be 0. Now you can pretty easily see that this would be 0, right? There would be no improvement having the document versus not having the document, having the null document. So if this is high, that means these retrieved documents are actually relevant. So you can see that if you do random uniform masking, then it's okay, it gets above 0, all right. If you do random span masking, it gets even higher. And if you do salient span masking, it gets very high. So again, you see here the difference between the salient masking and the others is, I would say higher than the difference between not having the document at all and doing the random uniform masking in pre-training. So again, something to think about. At last, they have one example right here where they can show that actually helps. This is just a concrete example. So the question here is, an equilateral triangle is easily constructed using a straight edge and a compass because 3 is A and then blank prime. So this is the masked word right here. If they just ask the model what it should fill in, the probability, and Fermat is the correct answer, is super duper low. Okay. Then if they give it the correct document, right, they just search out the correct document, which is here the conditional probability with this document 257 is a Fermat prime, thus a regular polygon with 257 sides is constructible with compass. So you can see that it has some overlap, like the constructible with compass. Okay, the constructible with compass, it's not an exact overlap, so it's debatable whether a classic search engine would find this, probably, but not. And then the A something prime, they are here. So given this document, you can see how a model could easily classify Fermat as the correct answer. And in fact, the probability is, I guess it's not 1.0, but it's a rounded 1.0. So if you give the model, the model 3, if you give it the relevant document, it immediately knows what the answer is. And if you give the if you do this whole retrieval step in between, so this is marginal probability marginalizing over the top 8 retrieved documents. So now they don't tell it what the correct answer is, but they actually let it do its whole retrieval thing and marginalize over the top documents. then it still assigns a very high probability, and I'm going to guess that's the top probability for all of the words. But you see there is a considerable decline, so it's not like it's always super sure. And I think there is quite a bit of improvement still to be done right here, because as a human, if I go look for an answer for this question and I find, even if I consider the top 8 documents, I don't think they would confuse me to the point where I'd say that Fermat is only 12% likely, even though it might be more likely than any other word. I would assign it probably a much higher probability. So I think there's a bit of improvement still to be made right here, and I'm looking forward to what people can come up with. All right, I hope you enjoyed this video. I know it's been a bit of a long rant, but I wanted to make sure the individual parts are clear. Let me know what you think of it, of the model itself, and I wish you a good one. Bye-bye.